Alright, so in order to get any information about any physical system, in particular quantum systems in this case, we have to observe the system. So we need to perform a measurement. And in our course, we will only consider projection measurements. Now, suppose that we are given a qubit psi in the canonical basis, alpha 0, 0 plus beta 0, 1, okay, such that magnitude square alpha plus magnitude square alpha 1, such that magnitude square alpha 0 plus magnitude square beta 0 is equal to 1. Now, any measurement on psi will cause this qubit to decide which one of the basis states that it will remain in, either 0 or 1. So then the measurement we're doing here can be considered as a projection onto one of the basis states. So we have a vector, so let's suppose that these two axes represent the basis states, ket 0 and ket 1. Suppose that we have a vector psi in a superposition, and suppose that we have an angle of theta between psi and ket 0. After measuring psi will be projected onto one of the basis states. It's going to get projected onto ket 0 with probability magnitude alpha 0 squared, or it's going to get projected onto the basis state 1 with probability magnitude beta 0 squared. Okay, or if we know the angle theta, this is cosine theta, right? This is sine theta. So then the probability of observing 0 as the measurement outcome is cosine squared theta, and the probability of observing 1 is sine squared theta. So we can think of a measurement as a projection onto one of the basis states of the system. Okay. Now, good thing about quantum systems and any physical systems actually is that we can measure in any set of basis states which are mutually orthogonal to each other. Okay, so not only can we measure on the canonical basis, but we can measure in any set of orthonormal basis states. So consider the set of basis states. Suppose that U is 1 over square root 2 ket 0 plus 1 over square root 2 1. And suppose we have a vector which is perpendicular to U. Let's denote this by U perp 1 over square root 2 ket 0 plus 1 over square root 2. So this is supposed to be minus 1 over square root 2 ket 0 plus 1 over square root 2 ket 1. Now if we draw these vectors on a two-dimensional plane, so this is ket 1. Let's suppose that this axis represents ket 0. So U is simply this vector, right, which makes a 45-degree angle, pi over 4. This is U. And suppose that we have an arbitrary superposition, like something like that, maybe psi, which makes an angle theta with u, let's say. And then u perp is the vector which is perpendicular to u. This is u. Okay. Again, the angle is pi over 4. Now, if we measure psi in the u perp basis, okay, so let's measure, and I'm using the term measure in the intuitive sense here. We're going to formalize later. So let's measure psi in the u perp basis. Okay. Now we get, as an outcome, we get u with probability what? With probability cosine squared theta, right? Or we get u perp with probability sine squared theta. Okay, so the probability of seeing psi in the u basis state is determined by the square of the inner product of psi and u. Okay, and that's the angle was theta, the angle between psi and u. So the probability of psi collapsing onto u is cosine squared theta. Okay. So measuring in any arbitrary basis provides us to write any state psi in that basis. Okay. Now consider a similar set of bases, which we will call the sine basis. So this is called the sine basis. The sine basis consists of two vectors, as usual. Plus is 1 over square root 2 ket 0 plus 1 over square root 2 1. And ket minus is defined as the same vector except that we have a negative phase. So we have 1 over square root 2 0 minus 1 over square root 2 1. Okay. So ket plus is basically u here. So this is also equal to ket plus. Ket minus is the opposite direction of u perp. So it's this vector. Ket minus. Okay. Okay, so notice that the vectors in the sine bases are orthogonal to each other. Okay. And they are normalized. Now, after measuring, the probability of seeing psi in state ket plus is basically the square of the inner product of psi and plus. Right? So let's write that down. Okay, so suppose that psi is, let's say, 1 over 2 ket 0 plus square root 3 over 2 1. Okay, so it makes a 60-degree angle with ket 0. Okay, so ket plus is equal to u, which is basically this vector, right? So what's the inner product of psi and u? And we're going to take the square of that product. So the square of the inner product of psi and ket plus is simply 1 over 2 times 1 over square root 2 plus square root 3 over 2 times 1 over square root 2 squared, which is equal to 2 plus square root 3 over 4. So the probability of observing psi in state ket plus is exactly 2 plus square root 3 over 4. Okay, so how do we write psi in the sign basis then? So we want to write psi in this basis. So psi is written in the canonical basis here. Okay, so let's rewrite psi again. So psi in the canonical basis is given as 1 over 2 ket 0 plus square root 3 over 2, 1. All right, but then suppose that we want to write psi in the sign basis, okay, in the plus minus basis. So how do we do that? Well, to do that, we first need to, so psi will be in the form, suppose we want to write so psi will be in the form alpha plus beta minus, right? So we need to figure out what alpha and beta are. Well, for this we can write the canonical basis in this sign basis. So 0 will be in fact 1 over square root 2 plus 1 over square root 2 minus, right? If we take a look at the diagram here, right, so 0 is exactly between ket plus and ket minus in the positive direction for both vectors. What about ket 1? Well, ket 1 will be equal to 1 over square root 2 plus minus 1 over square root 2 ket minus. So then substituting these two in this equation, right, psi will be equal to, in this equation. So let's substitute ket 0 and ket 1. So we have 1 over 2 times ket 0, which is this vector, plus we have square root 3 over 2 times ket 1, which is 1 over square root 2 plus minus 1 over square root 2 ket minus. And this is equal to 1 plus square root 3 over 2 times square root 2 ket plus 1 minus square root 3 over 2 times square root 2 ket minus. Okay, so this is how we write any vector in the sign basis or any other basis if we were given another set of basis states. Of course, the basis states should be orthogonal to each other. Okay. So this is the change of basis. Change of basis. What we did here was simply a change of basis. And in physics, we do this quite often, actually, right? So let's suppose that we have a ball rolling down the ramp, right? in this direction. So suppose that we want to measure the speed or the velocity, the momentum of the ball. Now, instead of picking this basis, it's more natural to pick this basis, right, in the direction of the inclination of the ramp, right? So change of basis will be used quite frequently in many quantum algorithms. We will talk about this later again when we talk about quantum algorithms. Okay, so let's turn to the question now. Well, what do we measure in quantum systems? Entities do we measure? And we measure, obviously, observables. We measure observables. But what's an observable in quantum physics? It's straightforward to define observables in classical physics. An observable is a quantity, like temperature, velocity, momentum, position, and so forth. But what is an observable in quantum physics? Well, postulate of quantum mechanics tells us that an observable is, for every observable, there corresponds a matrix called Hermitian matrix. So let's give a definition. An n by n matrix A is Hermitian if A adjoint equals A. So it's A is self-adjoint, okay? We can give many examples, but maybe one example would be the matrix maybe 5, 4 plus 5i, 6 minus 16i, 4 minus 5i, 13, 7, 6 plus 16i, 7, minus 2.1, let's say. So this is a Hermitian matrix. I left a verification for you. So in quantum mechanics, given an n-dimensional quantum system, an observable is an n by n Hermitian operator. Okay, and note that by definition, the diagonal entries of a Hermitian operator must be a real number, right? Because we're taking the self-adjoint, we're taking transpose conjugate, and so that means the diagonal entries must be all real values. Okay. All right, so we have a couple of properties of Hermitian matrices. The details are given in the lecture notes, but let me write them as propositions. So if A is an n by n Hermitian matrix, then for all n-dimensional complex vectors, for all v and v prime in C to the n, we have the property that the inner product of AV and V prime is equal to the inner product of V and AV prime. Okay, so if A is a Hermitian matrix, then we can change sides of A without taking the complex conjugate. Now, this is one property of Hermitian matrices. The proof is in the lecture notes. Another property is that all eigenvalues of a Hermitian matrix are real. Eigenvalues of a Hermitian matrix are all real values. Okay, and finally, if we are given a Hermitian matrix, another proposition, given a Hermitian matrix A, distinct eigenvectors of A, which have distinct eigenvalues, must be orthogonal. Distinct eigenvectors of A, which have distinct eigenvalues are orthogonal to each other. So these eigenvectors must be orthogonal to each other. Now, this orthogonality has some physical meaning, in fact, because due to Heisenberg's uncertainty principle, we can only measure, say, either the position or the momentum of a subatomic particle, an electron or, say, hydrogen atom. So we cannot measure both quantities at the same time. So that's why this is the mathematical interpretation, that these quantities, and we will mention that, in fact, the outcome of the measurement will be one of the eigenvectors, one of the eigenvalues of the observable. So these eigenvectors should be orthogonal to each other simply because that we cannot measure two distinct quantities at the same time. All right? Okay, so next we will talk about the spectral theorem and the mathematical framework for establishing, for describing a basis for measurements and measurement outcome. So I'll see you in the next video.